right, section 2.2, set operations. So last time we talked about sets. What is a set and different ways of writing sets. We talked about power sets, cardinality, Cartesian product. Okay. So now we're going to get into things like union, intersection, complement. Any of you that took statistics, you will have already seen a lot of this stuff. Not all of it, but a lot of it. And this is one of those times when I have to remember which class I'm talking to because different books use different notation. Okay, I never got around to animating this. So if you have two sets A and B, the union of those two sets is everything, all the elements that are in either A or B or both. So in other words, about set builder notation. A union B is the set of all X such that X is an element of A or an element of B. And the word or in math and maybe also in computer science usually by default is the inclusive or, right? So it means one or the other or both. So if you have any elements that belong to both sets, they're also in the union. Okay. On the other hand, you have the intersection, and the intersection looks like this, A intersect B. Those are only the elements that belong to both sets. It's kind of the overlap of the two sets. X is an element of A and also an element of B. Okay. So the difference is the union is everything that belongs to at least one of the sets, and the intersection is only those things that belong to both sets. Okay? If two sets are completely separate, they don't have anything in common, those sets are called disjoint. So disjoint means that A intersect B is the empty set. Talked about the empty set last time. All right, and then, this is something I don't get to talk about in most of my classes. We don't do anything with this one. Set difference. So the way to think of this is like start with everything that's in A and then take out the things that are also in B. So the set of all X such that X is an element of A but not an element of B. Okay, that's called the set difference, and also called the complement of B with respect to A, and I will probably never call it that because I would be too worried about trying to remember where does the A go and where does the B go in that term. So I'll always call it the difference. A, and I might even call it A minus B, although I'm not 100% sure if that's correct to call it that, but all right, so those are different set operations, union, intersection, and difference. Disjoint is not an operation, it's just a description. Two sets are either disjoint or they're not. Okay. All right, and then it's kind of interesting they saved this one for last. Well, I can kind of see why they did that. So let U be a universal set. Now, I don't think I ever told you what a universal set was. A universal set is just any set that contains all of the objects that are sort of currently under discussion. All right? And so just skip down to the example really quick. So notice that they're making sets. A is the set of sophomores. B is the set of discrete math students. A logical universal set for that problem would be the set of all students at your school. All right, it's the set containing everything that we're going to consider in that problem. All right, and so if you have a universal set, the complement of the set A, which your book, and this is where I have to remember what class I'm talking to, looks like that. So A with a bar over it. That's everything that's not in A. Set of all X such that X is not an element of A, but is in the universal set, right? You need a universal set, in order to, there's lots and lots of stuff that's not in any given set, right? I could talk about A is the numbers 1, 3, 7, and 8. And unless you tell me what the universal set is, I don't know what's in the complement. I would guess that 2, 4, 5, 6 are probably in there. But what else is not in there? Maybe 9, 10. Where does it end? Wednesday, cheese, Winston Churchill. We have to know what are all the things that we're talking about. Maybe the numbers 1 through 10. Okay, no problem. If it's the numbers 1 through 10, the complement would be 2, 4, 5, 6, and 9 and 10, right? So that's why you need a universal set. Okay. So the example, suppose that A is the set of sophomores at your school, and B is the set of students in discrete mathematics. Express each of these sets in terms of A and B, all right, using things like union, intersection, complement, difference. Okay. So the first one is the set of students at your school who either are sophomores or are taking discrete math. Okay, so what does that sound like? A intersection? What do you think? It's union, right? So the key word is or. Since it's or, that's union. Okay. There's a couple different ways you could write number 2. The set of sophomores at your school who are not taking discrete mathematics. Well, that's kind of exactly why they invented this notation, A minus B, the set difference. Now, one of the reasons that we don't really have to talk about set difference is you can actually write set difference in terms of just the other symbols that you have over there. So if we want everybody who is in A and is not in B, and this might come in handy at some point because we're actually going to be doing some proofs with sets. If you ever have to do a proof involving set difference, it might come in handy to notice that A minus B is the same thing as A intersect B complement. Right? It's the set of everything that is in A and is not in B. Does that make sense? All right. Some identities, and I think we might actually prove some of these. When you look at this table, you might notice that you have a little bit of deja vu. It looks kind of familiar. And that's because a lot of these identities have the same names and are also very similar to identities that we saw in logic. All right? In a lot of ways, when it comes to comparing sets and logic, union acts a lot like disjunction, which makes a lot of sense because they both sort of mean or, right? And intersection is a lot like conjunction. And complement is a lot like negation. That line just by itself looks kind of funny. Complement. Okay. All right. So, so for example, De Morgan's laws. You have De Morgan's laws for sets. It says the complement of A intersect B is the same thing, is equal to, remember equality of sets means they contain exactly the same things, A complement union B complement. All right? And that is an awful lot like That's an awful lot like this. The negation of P and Q is equivalent to negation P or negation Q. Right? This is just like this. Okay. And there's different ways to prove these, and one of them looks a lot like a truth table. I'm going to show you both. Okay. Here we go. So the first thing they want us to do, prove the first absorption law from Table 1. And they very kindly pointed out what that is. So the union of A and A intersect B is equal to A. Okay. Now they don't say how to do that, but if you skip down here to letter B, these are sort of the two major ways of proving that sets are equal. You can either show that each set is a subset of the other, and I know I mentioned that to you the other day. You can prove that A equals B by showing that A is a subset of B and B is a subset of A. Okay. All right. So I think I think maybe that's how I'll do letter A. I'll do it that way. Let me see. I'll roll this up, give myself a little bit more room. And then maybe after you see me do letter A, you can do this one, or at least try it. All right, we'll have a little working break. Okay, so letter A, we want to prove that the union of A and A intersect B is equal to A. Okay. Well, I'm going to do the easy part first. So you have to show two subset relationships. All right? So I'm going to pick the easy one first. First thing I'm going to do is show that A is a subset of A union A intersect B. Okay. All right. Now, remember what subset means. Let me remind you that A is a subset of B if, for all x, did it quit again? That's weird. Please stand by. It's just not following me. Okay. Well, here, we could do this. Move it back a little bit so that it's... Now it can see the whole board. Mm-hmm. And it's blinking on there. Anyway, that's okay. All right, so A is a subset of B if for all x, x is an element of A implies x is an element of B. So the way that you show that one set is a subset of the other is you start with an element in what you think is the smaller set. So let x be an element of A. We must show that x is an element of A union A intersect B. And that turns out to be super, 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 super easy. Okay? Since x is an element of A, I'm going to say this, and you might think, well, yeah, duh. since x is an element of A, that means that either x is an element of A or, and I can write whatever I want after the or, right? That was a logic law. It was called, it wasn't called simplification, it was the other one. Addition, thank you. Remember, P implies P or Q, or something like that. Since x is an element of A, that means either x is an element of A or x is an element of A intersect B. All right, so that's addition, the logic law of addition. Okay. And this right here is the very definition of it belongs to the union. X is an element of A union A intersect B. This is an example of it's so easy it's hard. It's one of my favorite math rules. It's so easy it's hard. I blew that problem because it was too easy. I thought it was more complicated than that. Okay. That's the easy side. The other side is also easy. It's just maybe a teeny bit, couple of extra lines. Okay. So now we're going to go the other way. So now we have to show that A union A intersect B is a subset of A. Okay. So we start with an element in the first set. Let X be an element of A union A intersect B. We have to show that X is an element of A. So this is going to start to look kind of like a proof by cases. Okay? Because X is an element of A union A intersect B. That means, since X is an element of A union A intersect B, we have either X is an element of A or X is an element of A intersect B. That's what it means to be in the union. Okay. All right, so two possibilities. Either X is in A or X is in A intersect B. Well, if X happens to be in A, we're done. Right? We're trying to show that X is an element of A. All right? So if that happens to be true, then we're done. Otherwise, it must be that X is an element of A intersect B. So what does that mean? If X belongs to A intersect B, that means it belongs to A. What's the next word? Is it or? It's and, isn't it? If X belongs to A intersect B, that means it belongs to both A and B. Okay, and this is the rule called simplification. If P and Q are both true, that means, well, in particular, P is true. So, X is an element of A. We're done. This is a subset of this. And we already showed that it goes the other way around, so those two sets must be equal. Okay, I'm going to say it again. I've said it like 5 times. Proofs are not easy. I know this. It takes lots and lots of practice. All right? The good news is that there is another way to show sets are equal. And on the exam, I think you'll see when you look at last year's exam, there was one where I had you do it this way, and then I think there was another one where I have you do it this other way. You might like the other way better. All right. Okay, so it is 1:51-ish. So what I would like you to do during the next 10 minutes or so is try to do this one for letter B. Try to write this kind of proof. It's going to be a little different because we have some complements involved. All right, but just try. Okay? And then we'll go over that, and after we go over that, I'll show you how the membership table works. Hello? Okay. All right, so hopefully you tried at least B number 1. Okay, so showing the first of Morgan's law using each side as a subset of the other side. So let's go over it. The complement of A intersect B is equal to the union of A complement and B complement. Okay, so first we're going to show that the left side is a subset of the right side. I don't think for this one either of these directions is particularly easier than the other. They're probably the same. Okay, so if we're going to show that the complement of A intersect B is a subset of A complement union B complement, we want to start by saying let X be an element of A intersect B complement. We want to show that X is an element of A complement union B complement. Okay, well, since X is an element of A intersect B complement, that means X is not an element of A intersect B. Okay, so it's saying that X does not belong to both A and B. Since X does not belong to both A and B, that must mean it either doesn't belong to A or doesn't belong to B. I'm writing it out in words right now because I feel like that'll help make it clearer. You wouldn't normally have to do that. Okay. Well, that right there is kind of the very definition of A complement union B complement. i.e., X does not belong to A or X does not belong to B, which means X does belong to A complement or does belong to B complement. And therefore, it belongs to the union of those things. Right? It's pretty easy once you get the hang of it. Okay. So that's one direction. We showed that the complement of A intersect B is a subset of A complement union B complement. So now we got to go the other way. And once we show it works the other way, then we will have that they're equal. Okay, so now we want to show that A complement union B complement is a subset of the complement of A intersect B. Yeah?
The flare of the light is right there, and I can't make out.
Oh.
So if you get to the left and to the right, but exactly the direction.
So this right here, like Where should I not write?
Yeah, your hands are directly, just from the right side.
Like about there?
Yeah, that's fine to be in, but then to the left of that.
Oh, okay. So like right about here, I shouldn't. Okay.
Yeah.
This okay?
Yeah.
Okay. Oh, okay. That's a funny picture. All right. All right. So let X be an element of A complement union B complement. That means either X is an element of A complement or X is an element of B complement. So I think this is going to kind of go by cases again. All right? If X is an element of A complement, then X is not an element of A. All right? Okay, and so how do I say this? I want to say that since X is not an element of A, it can't possibly be an element of A intersect B. All right? Well, I think I'm just going to say that and try to convince you that it's true. Because think about what A intersect B is. It's the set of everything that belongs to both A and B. How could something be in both A and B when it's not even in A? Right? Therefore, X is an element of A intersect B complement. And you can say the same thing about B. All right? You know, there's no guarantee that X is an element of A complement. It might be that X is an element of B complement. All right? Well, if that's the case, same thing. If X is an element of B complement, then it is not an element of B, and so it can't possibly be in both A and B. Okay, in either case, X is an element of the complement of A intersect B. And that's it. Okay. Left side's a subset of the right side's a subset of the left side. The two sets have to be equal. Okay. So take that in for half a minute, because now I'm going to show you how to do the membership table. I think you're going to like that. I wish I could do it over there, but that podium is in the way, and then the people over there can't see. I would love to see the extra whiteboard that you were telling me about, and it would also be cool if, you know, I teach in all sorts of different classrooms, and some of the classes I teach in I think maybe this is only at Stanislaus that I have this. The screen is actually over in the corner, so it doesn't block the whiteboard, which can be a good thing or a bad thing, because sometimes I want to draw on the things that are being projected. So, what would be really cool would be one you could slide around. You know? Put it on a track. All right. Everybody pretty happy with this? At least makes sense? Okay to get rid of this? Okay, so now we're going to do the membership table. Unfortunately, you can't use a membership table. Well, maybe there's a way to do it. I'd have to think about how, though. For subsets, because in letter C, we're just going to show that this is a subset of this. I don't know how to do that with a membership table. Actually, I think I do know, but anyway, I'm going to do it the other way for that one. Okay, a membership table is a lot like a truth table. Okay, so here's how it works. You're going to love this. It has ones and zeros in it. Suppose it could have T's and F's. Okay, so in a membership table, you use ones and zeros to denote whether or not something belongs to the set. Okay? And so you guys normally do this like 0, 0, 1, 1, and then 0, 1, 0, 1, right? Okay. All right. And so, first thing I'm going to talk about is, remember we're using this for complement of A intersect B equals the union of A complement B complement. So first I'm going to write A intersect B. Now the only way something can belong to A intersect B is if it belongs to both sets. So that means the only place under A intersect B that I'm going to put a 1 is when they both have 1s. Right? If an element belongs to both A and B, then it belongs to the intersection, otherwise it doesn't. And so these are all going to be zeros. So when you take the complement of that, everything flips to the opposite. 1, 1, 1, 0. Okay? So now I'm going to compare that to what I get for A complement union B complement. All right, so over here I'm going to say A complement is exactly the opposite of what I have under A. Instead of 0, 0, 1, 1, it's going to go 1, 1, 0, 0. And under B complement, instead of 0, 1, 0, 1, I'm going to have 1, 0, 1, 0. And something belongs to the union of those as long as it belongs to at least one of them. So for union, you only put a 0 if they're both 0, which only happens right here. All these other ones get a 1, because that means it belongs to at least one of them. All right, and so once you show that the two columns are the same, that means those two sets are equal. Yeah? Exactly. Intersection. Yeah. All right. That's pretty easy, right? It's just like doing a truth table. Which one is?
The one that's always a 0? The only time that you put it if it's all zeros?
That's union. Yeah. Because what it's saying, 0 means it does not, element does not belong to the set. If it doesn't belong to this set and it doesn't belong to this set, it doesn't belong to the union. But in any other case, it belongs to at least one of the sets, and so it does get into the union. Okay? All right.
Would that be like sufficient enough for like a test or something?
Well, okay, so if you look at last year's test, what I did, I had like 2 set equality problems, and I had you do one of them this way, and I had you do the other one this way. Okay. So now, okay. Stay away from here. All right. Letter C. Show that A minus B minus C is a subset of A minus C. All right. So this is nice. It's half the work of a set equality problem. You only have to show it the one way. let X be an element of A minus B minus C. So remember the definition of set difference. A minus B is the set of all X such that X belongs to A but does not belong to B. I don't think that's the same way I said it last time. I mean, it means the same thing, but I think we said it like that last time. Okay. Well, if X is an element of A minus B minus C, I want to break this down, kind of gradually. That means that X does belong to A minus B and does not belong to C. Okay, well, if you break that set difference down one more time, this right here says that X does belong to A, does not belong to B, and just carrying this down, does not belong to C. Yeah?
A minus B, isn't this essentially A? Isn't some type of rule? Like A minus B is because if you know the elements in B are in A, then you just have A.
That's a special case. Yeah. Okay. So it doesn't work for sets in general, but if your sets A and B happen to be disjoint, so like here's A and here's B, okay, start with everything that is in A and then take away the stuff that's in B. Well, you're not taking away anything because none of this stuff is in A. And so what you're saying is that A minus B is the same thing as A, but that's only true if A and B are disjoint. It's not true in general. You know what? Maybe it would be nice to have a specific example. Let me do that real quick. So suppose that A was the numbers 1, 3, 4, and 6, and B is the numbers 2, 3, 6, and 8. Then A minus B, you just take all the stuff that is in A, you take all the stuff that is in A and you take out the stuff that's in B. And so 3 and 6 are both in B, so they have to come out. The 2 and the 8 don't do anything because they weren't in A to begin with. So then A minus B would just be 1 and 4. So in this case, it's not the same as A, right? Okay, I'm glad you asked that, though, because we really should have done a specific example. It's kind of hard to see if you don't have that. Okay. Well, in terms of this thing, once you break it down like that, it's pretty easy to see why that X has to be a member of A minus C. See, A minus C doesn't really have anything to do with B, right? So all I'm going to say now is that since X is an element of A and is not an element of C, that is exactly the definition of A minus C. See? I just had to get rid of the stuff about B because that doesn't matter. Yeah?
It looks like a simplification step you're doing there.
Yeah, kind of. It's sort of like saying... It kind of does look like simplification. It's kind of like saying P and Q and R implies just P and R. Yeah, exactly. Okay, so that's it. That does it. We started with an arbitrary element of the first set, and we showed that that has to be in the second set. So first is a subset of the second. All right. Kind of sort of makes sense? That wasn't hard. Like I said, it's about half the work of showing sets are equal. Oh, fun stuff right here. Here we go. Take a break from the glare for a little bit. Generalized unions and intersections. I never get to talk about these in any of my other classes. Sometimes you want to take the union or the intersection of a whole bunch of sets. And us mathematicians being lazy, we came up with a shorthand notation for that. One of these days, if I ever, manage to think about it when I'm not in a hurry, it irritates me that my Microsoft Word, anytime I have to type something that has indices on it, an index, for those of you who know Calc 2 or even end of Calc 1, definite integrals or even limits from the beginning of Calc 1, I can never get them to go directly under and over, whatever it is. In the equation editor, it looks like it is supposed to go there, and then it never ends up there. I have a vague memory once of seeing where you could change some setting to fix that, and I don't remember how it works. Anyway, when I write it on paper, it normally looks like this. So when you see the union of a sub I for I going from 1 to n, that just means A1 union A2 union, etc., 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 all the way up to a sub n. So there's some mystery number of sets there that we're taking the union of. Ditto for intersection. Okay, and so I think for that I just have a couple of examples of finding these unions and intersections, like this one here. Okay, this is a fun problem. So a sub I is basically the set of integers up to and including the number I. Integers up to and including the number I. Okay. So for example, well, put it this way. A1 would be the set of all x such that x is an integer and x is less than or equal to 1. Remember, this means integers. A2 would be the set of all x such that x is an integer and x is less than or equal to 2, etc., etc., etc. All right? Integers up to and including I. And so, if you want the union I going from 1 to n, a sub I, all right, that means you're taking the union of A1, A2, all the way up to a sub n. So what we have to think about right now are what are the numbers that belong to at least one of those sets. As long as your number belongs to at least one of those sets, it gets into the union. Okay. Think about it for half a minute. So this is integers up to and including 1. This is integers up to and including 2. Da 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 da. Integers up to and including n. And so if you want all the numbers that belong to at least one of those sets, you would be talking about integers up to and including what? Those would definitely all be in there because they were in every single one of those sets. Okay. Anything else? What's the biggest number that occurs in at least one of these sets? I'll give you a hint. It's not a specific number. It's a. It's not I. See, I is what we call an index.
Is it?
Yeah, it's n, right? See, when you write this out, you don't see the I anymore. I is called an indexing variable. So the only place we use it is over here, just to say I is going from 1 to n. sort of like looping or something. It is n. The biggest number that's in any of these is n. In fact, I could draw you a picture. The union of all these sets is actually just the set A sub n. Okay. Let me draw you a picture of the Venn diagram for that, because it's kind of nice. Okay, here's A1. A1 contains all the integers less than or equal to 1, including all the smaller ones, -3, -4, -100, right? And then if you draw a bigger circle outside that, A2, the only thing that brings into the picture is the number 2. And if you draw a bigger circle outside that, only thing that brings into the picture is the number 3. And you can do that as many times as you want. Up to n, and then the only thing that you didn't already hit is the number n. And so if you take the union of all those sets, you're just taking absolutely everybody that belong to any of the sets. Okay? So the union of all those sets is exactly the set A sub n. Okay? What would the intersection be? What are the numbers that are in all of those sets? What is it? Only everything up to 1. That's right. You get just even up to the number 2. The number 2 is in almost all of these sets, but it's not in A1. Well, the second you miss one of the sets, you don't get to be in the intersection. Okay, so this is the intersection right here. It's just the smallest one. Okay. The intersection is A1. The union is A sub n. All right. Make sense? And that's all I got.